So let me hit you up with a few brief announcements and then introduce our guest lecturer for today. As a reminder, you do have lab this week. Please go. Be the last lab. Also, please don't forget to turn in your homework this week and your project 3. They're all due this week. And a final announcement. Today is the last day we'll be accepting requests for a change to your final exam format. So if you forgot to respond to requests to take it online or to switch to in-person, today, last day, please RSVP on the Google form we've posted. All right, so it's my pleasure to introduce Professor Ziad Obermeyer. Ziad trained as an ER doctor and still practices from time to time. But today his primary job is as a professor in the public health school, doing research and teaching. And he studies how to use machine learning to help doctors make better decisions, and also what can go wrong when you use machine learning in that context. So we're really looking forward to his lecture, and I welcome Professor Obermeyer.
Thank you so much. Let me get my slides up. All right, so it's really a pleasure to be here because I think that I teach a class on artificial intelligence applied to health and healthcare, but I think that classes like this one are really such an important part of the pipeline for getting the kinds of skills that I think everybody needs in all walks of life into domains like health, where historically we haven't had a lot of competency in data or math. As David mentioned, I did go to medical school, and I think I knew less about math after medical school than I did going into medical school. So I'm hoping that classes like this one will actually start getting more data and math competency into the pipeline for people who are going into fields like medicine. And drawing on that, I just wanted to start with an observation about where I think algorithms fit into healthcare, which is that there are many, many great uses of algorithms in health. I came into this research because as a doctor, when you're practicing medicine, and if you're paying any attention at all, you are constantly making mistakes, and those mistakes are very, very painful for everyone involved, most of all the patient, of course, but also for you. And algorithms have a ton of potential for helping us make better decisions and avoid mistakes that are very, very costly in health. Mistakes around risk prediction, trying to figure out, okay, this is a patient in front of me. I observe this data about them. What is going to happen to this patient? What do I need to do about that now? Diagnosing people with certain illnesses. All of these things are great jobs for algorithms because they involve processing a very complex set of data into a probability estimate, for example, of the likelihood someone's having a heart attack. But at the same time, as I've learned from some of my own research, there are lots and lots of ways that algorithms can go horribly wrong. And in particular, the things I want to talk about today is how they can reproduce and even scale up biases and inequalities and structural problems that affect our healthcare system and end up making their way into algorithms. So I'm going to do that by telling you two stories about two algorithms. The first one is an algorithm that scales up racial bias that we studied in the context of one particular company's algorithm that was sold to hospitals around the country and affected important medical decisions for millions and millions of patients. And so I think of this as the kind of evil twin, but there's also a good twin, which is an algorithm that, by contrast, actually worked to fight against a particular kind of racial bias that was built into medical knowledge, but that doctors actually did not know about until this algorithm pointed it out. And along the way, I'll highlight one really important theme, which is that algorithms need to be aimed with great care. Algorithms are this amazing new ray gun that we have available to us, but they need to be pointed in the right direction. And if we point them in the wrong direction, they do a lot of harm. And if we aim them at the right target variable, if we predict the right thing and don't get misled by problems in our data set, they can be incredibly powerful and positive forces. I'll also highlight a lot of the applied follow-up work that we're doing to try to get the insights from the papers that we write out of the proverbial lab and into the real world where they can actually make a difference for real people. So let me start with the first one. This is an algorithm that is used to help health systems and insurance companies get extra help to patients who need extra help. So one thing that I think you all know about our healthcare system is that it doesn't work very well for everyone, and that there's this set of complex, chronically ill patients that have very high costs and also get poor care. So, you know, the stereotype you can think of is someone like with advanced diabetes who has to go to an endocrinologist and a cardiologist and a pulmonologist and all sorts of other doctors. Their care is fragmented, it's very expensive. They end up in the hospital because their medications get mixed up. And so what hospitals and health systems have started doing for those patients is what's called high-risk care management. It's not a very good name, but it's basically like extra help. You can think of it a little bit like it's like a VIP program for patients that really need help. So that patient, the very complex diabetic patient or someone with heart failure or emphysema, it's a one telephone number line that you can call and talk to a human that can come to your house and help you with whatever issue you're having. They can get you a primary care appointment if you need it. They basically just, they're like your concierge, and they do whatever it takes to keep you healthy, to keep you out of the hospital, and to both try to prevent your chronic illnesses from flaring up, but also prevent you from going into the ER and costing everybody a lot of money. So if this works well, everybody wins. But for it to work well, you need to pick the right people. So all of those resources are themselves expensive. And so you need to get those resources to the right people who are going to benefit from those resources, because you can't do it for everyone. There's a whole staff of people that it takes to make these programs work. There's extra primary care slots. So you need to target this. And that's where algorithms come in. So we studied a piece of software that hospitals use to help allocate that resource. And that specific piece of software was being used when we studied it for 70 million patients every year in the US. If you look at the family of algorithms that work like it, by the market estimates, those algorithms are being used for effectively the majority of the US population. So one point that I didn't know before I started doing this research is just how incredibly widespread algorithms already are in the healthcare system, and how they're already affecting really important decisions for millions and millions of people. What all these algorithms try to do is find patients who are going to get sick. And so this is, you know, as you know, something algorithms can be really, really good at. They're very good at predicting, you know, if you watch this movie, how many stars are you going to give it? If I show you this product, will you buy it? So that same infrastructure is basically ported over to healthcare, where algorithms trawl through a ton of the healthcare data that we have on a given patient and makes a prediction on whether they're going to get sick, as measured by, do they come into the hospital for ER visits and rack up a lot of costs when they do get sick. And those predictions about healthcare tomorrow are being used to target that extra help today. So if you're the kind of person that looks like you're going to get sick, according to that algorithm's prediction, then you're the kind of person who's going to get prioritized for access to this extra help program. Let me just, I'll pause for questions in a second, but let me just give you a slightly more granular way to think about how these algorithms are being used. So think about, there's some population of patients, and we studied it in a primary care system, about like 50,000 patients. And imagine that algorithm is just outputting a risk score for all those patients. So this happens a few times a year. The algorithm just generates a score based on all of the data that the algorithm has available to it when the score has generated it. And there's some distribution of scores. And there's some right tail of people who really look like they're going to get sick. And so that top 2% in the healthcare system we studied gets fast-tracked into the extra help program. So they're in. The next half, approximately, gets shown to their doctor. So this is like a human in the loop kind of design, where the algorithm flags people. That generates a list, and each primary care doctor gets shown a list of her patients that the algorithm has flagged as maybes. And then the primary care doctor gets to check off, you know, yes, this one would benefit from the program and this one would not. And everyone else gets screened out. So they don't get access to the extra help program. So basically, the algorithm score is determining how we're treating them with respect to this pretty important decision about, do you get, you know, extra help with your chronic conditions? Let me pause there for a second and just see if there are any questions about this general setup. And I'm just pulling up the Q&A and the, sorry, I can't answer any information about the final exam. Okay, please just turn your mic on, interrupt me if you have questions, or put it in the chat and I'll check periodically. Okay, we were interested in whether these algorithms contained racial bias. And one really important thing about measuring racial bias in an algorithm or anywhere else is that you have to be able to very crisply articulate what bias looks like or what fairness looks like so that you can actually measure it. So here's our attempt, and I hope this makes sense to you, and if it doesn't, please just chime in. So as I showed you, people who have the same score get treated the same way. They have the same likelihood of getting enrolled in this extra help program. So given that we're using that score to make a decision about who needs help with their health needs, two people with the same score should have the same needs. So that's what a fair algorithm would look like. And specifically, the color of their skin should not matter for that decision. It's just about the score. The score should find people who have the same needs. It should prioritize them at the same level. And we shouldn't care whether that person is Black or white or male or female or anything else. That is not what we found. So let me just walk you through this graph, because I'll show you a couple that look like this. So on the x-axis here, we have the algorithm risk score. So this is just like we took everyone in this population and we ranked them by the algorithm score. And we've drawn those thresholds that I mentioned. Here's the 55%, here's the 2% threshold. So that's on the x-axis. On the y-axis, we've got what happened to their health over the year after the algorithm made the prediction about who was going to get access and who wasn't. So what we did is we just looked at if you had an exacerbation of one of your chronic conditions, like your heart failure flared up and you went to see your doctor, your emphysema flared up and you went to the ER, you got a +1 on that measure. And then we just look at the average of that measure on the y-axis, but we do it separately for Black patients versus white patients. And let me just say a word about what that means. When you go into a hospital, they give you a set of checkboxes and you check off how you identify. So this is the patient's self-identified race, but as documented in like a checkbox. And so, so we have a limited amount of information, but it is how the patient identifies themselves. So the top line, the purple line, shows you the average health for Black patients over the year after that score was generated. And the bottom line, the gold line, shows you that same quantity for white patients. And what you can see is that the purple line is always above the gold line. And what that means is that there's bias in the score, because at the same score, no matter where you draw a vertical line, Black patients at the same score have on average worse health. So what that means is that white patients who are healthier are getting prioritized ahead of Black patients who are sicker for access to extra help. So there's bias in this algorithm score. How much bias is there? It's not immediately obvious from this graph. So let me just give you one statistic to tell you the scale of this. Let's just look at that fast track, that 2% of people with the highest risk scores who get prioritized into this program. When we studied this program and this algorithm, that fast track was 18% Black. And you might look at that number and think, oh, that's actually pretty good, because only 12% of patients in the whole population are Black. So actually, the algorithm is overrepresenting Black patients by 50% in the high priority group. Seems great, right? But if you took their actual health outcomes into account and you just equalized, we just want to treat people the same based on their health, not on their score, you would actually get a high risk group that is almost half Black. So this is a very large amount of bias that was being encoded in this algorithm. An important question, of course, is, so there's a question how I measure the realized health. This is that thing that I told you about. If you have an exacerbation of a chronic condition, you go in to see a doctor, we see that condition and we give you a +1 on that score, and we just add up all of those chronic conditions. So that's our measure of health. So where does that go wrong? We want to understand the mechanism, how the bias got into this algorithm. And one really important clue is where that algorithm went right. So I'm showing you now a very similar graph where algorithm score is on the y-axis, Black and white patients are here. But now instead of showing you someone's health over that next year, I'm showing you their cost. How much did they cost the healthcare system? And now you can see that actually the algorithm is predicting total healthcare costs very well and without bias for both Black and white patients. So now these lines are on top of each other. This y-axis is actually a log scale. So it's predicting cost extremely well for Black and white patients alike. So what does that mean? Well, it means that the algorithm is biased when it's predicting health, but unbiased when it's predicting cost. There's only one explanation for that, which is that Black and white patients don't have the same relationship between their health and their costs. Why might that be? Well, for reasons that you all probably know already. White patients have better access to healthcare. So we were studying an insured population. So this isn't about insurance, but there's a million ways in which, because Black patients have less resources and less access to the healthcare system, less access to transportation, harder to get days off of work, depending on what job you get. All of those things that disproportionately affect Black patients are going to affect their ability to get in, to get care, and that's going to decrease their costs, even at the same level of health. There's also just racism in the medical system. We know from a lot of studies that the healthcare system treats Black patients differently. Doctors are less likely to recommend care to them. The doctor-patient relationship is just a lot more complicated when the doctor is largely white and the patient is Black. So all of those things conspire to mean that two patients with the same health, however you want to measure health, are going to have different costs based on the color of their skin. So that's not just about race, but it's partially about race. It's about the correlation between socioeconomic status and race for access and resources, but it's also about racism itself. And all that means is that Black costs are lower, conditional on health. So if you train an algorithm to accurately predict someone's healthcare costs, you're also training it to be biased in how that algorithm is going to predict their health. And that's how this algorithm turned out to be so biased. There are a couple of lessons that I want you to take away from this for how you understand how to make sense of whether there's bias in an algorithm. You want to focus on the output, what the algorithm is producing and what it should be producing. So in this case, we were able to very crisply articulate what this algorithm should be doing. What is the information that that algorithm would provide to the decision maker? Well, we want to know how sick someone is going to get over the next year as a way to help allocate these resources for extra help with that sickness. That's what we think of as the ideal target, what the algorithm should be doing. And that's how we held the algorithm accountable. We looked at its predictions as a function of how well it was predicting that ideal target. And that's going to detect a wide range of biases. Failure to generalize from the training set to the test set, from the population in which it was trained to the population in which it's applied. But it's also going to detect this very insidious kind of bias that we studied, which we're calling label choice bias, because it comes from the choice to predict a label that is biased. In this case, the algorithm designers chose to make the algorithm predict healthcare costs as a proxy for health. But that is a bad proxy because not everybody with poor health generates cost in the same way. So remember, if we just looked at the algorithm's ability to predict cost, we would have concluded that that algorithm was unbiased. And we had to look at its ability to predict health to conclude that there was actually an enormous amount of bias in that algorithm. The second thing to remember is to not be distracted by all of the things that you might read in academic literature, in the media, about how you might hold algorithms accountable and make sure that they're biased in ways that I think are less productive. There are lots of rules of thumb about, oh, how diverse is my data set? And data set diversity is really important, but you can't tell how biased an algorithm is just by looking at the composition of the training set or the test set. You actually need some metric based on what the algorithm is producing to make a determination of whether or not it's biased. Similarly, had you just looked at the fraction of Black patients in that high priority group, you would have seen, oh, that Black patients are overrepresented relative to the general population. This algorithm doesn't look biased, when in fact, that was way too low for what it should have been relative to the health needs of those patients. Finally, I think in medicine especially, you're seeing a lot of movements to eliminate any kind of race-based correction. So any algorithm that adjusts the score explicitly up or down for Black or white patients is viewed as biased. And while those algorithms can certainly be biased, it's no guarantee of bias if there is a race correction. And in the algorithm that we studied, there was no race correction, and that did not stop the algorithm from being extremely biased. So all of these rules of thumb about the inputs to an algorithm are, for me, helpful for diagnosing what's going wrong, but very unhelpful for making the determination about whether or not an algorithm is biased. The last thing I'll say on a more optimistic note is that once you detect the bias, you can actually fix it. So when we first got these results, we actually got in touch with the company that makes this algorithm, and we alerted them to the problem. And we worked with their technical teams to actually fix the problem. We retrained the algorithm to predict a basket of measures related to patients' chronic illnesses, not their costs. And that dramatically reduced the amount of bias in the resulting algorithm by 84%. So we're able to fix the bias once we understand where the bias is coming from and how to retrain the algorithm on predicting things that are much more closely aligned to what the algorithm is supposed to be doing to begin with. Let me pause there and just take a quick look at the question. So there's a question about whether the graph means that the algorithm was not racially discriminating, but the people who acted on the algorithm were racially discriminating. No, I don't think so. So what we showed in that graph is that the score for a Black patient and a white patient could be the same, but what happened to that patient in the year after the algorithm score was very different in terms of their health. Now, there's a deeper question that's very similar to your question, which is, why was cost so biased? And that is the result of a number of human decisions. So if a doctor recommends less care to a Black patient, as we know they do in some settings, that decision is going to be built into the lower cost that Black patients have. And if the algorithm is predicting that cost, it's going to accurately deprioritize that Black patient because they look less sick based on measures of cost relative to what they would look like if we use measures of health. There's another question about how that 84% was calculated. So what we looked at there in collaboration with that technical team was looking at conditional on the score. So if we look at two people at the same score, and we go back to, for example, the graph that I showed you here, one way to, as a summary statistic, to get to the bias of this is to condition on score and look at how many excess chronic conditions Black patients had relative to white patients. So you can just think of that as like the difference between these two curves, conditional on each score. That generates a statistic of like extra illnesses in Black patients conditional on score. And that's the number that went down by 84% with the new algorithmic prediction. In the paper that I think we can probably link, we show results for some other races. The sample sizes were smaller than for Black and white patients. Those were the two largest groups. And so, one really general problem with doing research in areas that look at smaller groups, and that includes intersectional groups with different identities, is that the sample sizes get really small and your ability to make firm statistical conclusions just gets mechanically lower. And so that's just a problem with that research in general that I think is a really interesting and fruitful area for future research. Couple of other questions. Is it necessary for an algorithm's bias to have real world consequences before it's caught? No, I certainly hope not. So I think that a lot of the work that we've been doing that I'll describe in a second tries to speak to both this question and the question of how do you come up with an ideal target? So let me talk about that for a second and see if that answers your questions. So we got a lot of media coverage for that initial study. And what we tried to do is turn that publicity into collaborations with a bunch of different types of organizations in healthcare and also outside of healthcare. So insurance companies, healthcare systems, tech companies that were making algorithms for healthcare systems. And so a lot of those organizations approached us to do audits of their algorithms because they were very concerned that their algorithms were similarly encoding biases like the one that we found. And the bad news is that we found a lot of bias in almost every algorithm that we looked at, whether that was being used for these kinds of population health decisions, whether it was being used to predict whether someone is going to develop diabetes, whether that was used to optimize the primary care clinic schedule by rebooking appointments for patients who were unlikely to show up. So in this playbook that I think is linked on the class website, you can find those stories and how we detected the bias and how we fixed it. The bad news is that there's a lot of those biases. The good news is that they're fixable by going through a similar process to the one we did for this algorithm, which is really trying to understand, what is this algorithm being used for? What's the decision that the algorithm is being used to improve? So in our setting, the one I just told you about, it was a decision that was fundamentally about helping people with their health. So how would we ideally want an algorithm to help us with that decision? Well, by finding people who need help with their health. So that process of understanding the decision, who's the decision maker, what patients is this affecting, what would we want that algorithm to do? It's not an easy process. It's a very semantically intensive process that requires you to know something about the setting where the algorithm is being used. It's not something that you can kind of automate with a Python or R package that's just going to spit out some metric of bias, because, as you saw with this algorithm, if we just computed those metrics on the algorithm's ability to predict cost, which is the thing that the algorithm set out to do, we would have concluded that the algorithm was not biased. We had to engage in that process of understanding what the decision is, how that decision would flow from the algorithm's prediction, to understand that this algorithm should have been predicting health, but instead it was predicting this other thing, and that's where the bias came from. So I think that process can't really be automated or standardized. It requires a lot of deep engagement with the field and the area that the algorithm is being used in. And that's what makes it hard, but that's also what makes it really interesting. And I think it makes it particularly interesting for people like you. Not all of you are going to go on to be, computer scientists and algorithm designers, but you will need to be educated consumers of algorithms in your field, in whatever industry you're working in. You will be using algorithms. And that kind of thought process of, how am I using this algorithm? What is this algorithm doing? What does it mean for the algorithm score to be high or low? I think is going to serve you very well for catching all sorts of problems with those algorithms, including racial biases. So there's another question: wouldn't an algorithm that adds a correction factor for race be less discriminatory because it could explicitly change the data to be even between all races? Really great question. Absolutely. So you can easily imagine, I think everyone can imagine, how such an algorithm could be very discriminatory. Like, let's say that, a credit scoring algorithm just took several points off of the credit score because you were Black. That could be very discriminatory. But as Alexander points out, that can also be very fair. So in the health setting, if Black patients need more healthcare, then you would want an algorithm to adjust up their score based on race, because they do actually need more care. So it all depends on how that algorithm is being used, what decision it's flowing into, and how resources get distributed as a result. I wanted to also mention a couple of lessons, because many of you will be going out into the real world at some point. You will be working in a job inside of an organization, and you will be using or you will be exposed to algorithms. One of the things that we found from doing this work with real organizations is that there is often almost no accountability structure for algorithmic oversight anywhere in the organization. It's a very surprising thing, because algorithms are such powerful strategic tools in organizations, and yet nobody at the strategic level of the organization is responsible. There's nobody in the C-suite who oversees or is accountable for or even spends time thinking about algorithms, even though those algorithms are touching thousands or millions of their customers, patients, whatever. So there needs to be some sort of high-level responsibility for algorithms, not just for catching problems, but also for deploying them in intelligent ways. There's no inventory of algorithms in most organizations. Most organizations have no idea what algorithms are being used where or how. And that's very unlike how a lot of other organizations use very important tools. And the last thing that's very important that we found is that there's no systematic way to document algorithmic performance inside of organizations. So algorithms are not keeping track of how accurate algorithms are that they're using, or whether they're fair or not. And that's a huge problem for them, both because it's the wrong thing to do, but also because when a regulator, as with the kinds of state law enforcement officials or federal regulators that we've been working with as part of this work, when they come to do an investigation, it's a very bad look to not have any documentation about how your algorithms are performing and what they're doing. So let me just pause there and see if there are any other questions before I move on to the next algorithm that I wanted to tell you about. Oh, there was a question that I missed about how we conducted the research. So we worked with a healthcare system that had a big primary care practice and had bought the algorithm in question. And so that algorithm was actually sitting on the server along with all of the other health data that we had access to. And that's why we were able to study both how the algorithm was made, that it was predicting cost, and also how patients did, what their health outcomes were as a function of that algorithm score. And so that was a really important part of the work, was partnering with a hospital that had all of the data that we needed. There's another question about what I mean by oversight. So, in organizations, you've probably seen in some organization that you've interviewed for or worked with an organizational chart. And that describes basically like who is whose boss, what functions of the company sit within which person's purview. And if you look at that, there's no place where algorithms and algorithmic oversight fits in. There's no one person responsible for algorithms and their performance. And that means that there's no accountability, because unless a person is responsible for algorithmic oversight, then there's nobody responsible. And lots of bad things can happen with no strategic direction preventatively and no way to fix problems as they come up. So that's what I mean by oversight. There's another question about, did choosing hospital based on data availability bias our results? So it's a great question, and always one that's important to think about with research. What we were doing with this hospital was studying how a standardized commercial product, an algorithm that was being sold to hospitals across the country, that was a standardized software product, looked when we looked at health outcomes in one hospital. So is it possible that this hospital was not representative in terms of its health outcomes of other hospitals? Sure. We've since replicated this finding with a number of health insurance companies and other hospitals. And so that replicability is a really important part of making sure that the research is sound. And I actually hope that lots of other people try to replicate our results. All right, let me move on to algorithm number 2, the good twin. And I'm going to completely switch gears as far as a setting and tell you about pain. So pain is shockingly concentrated in the most disadvantaged people in society. So if you look at surveys that just ask people, have you been in severe pain in the last 24 hours? The rate at which Black patients, for example, respond yes is about twice the rate of white patients. And there are similar differences by socioeconomic status, by education. So pain is just this enormous and disturbing fact of life for a lot of people, and the people who are already least privileged by our healthcare system and our society to begin with. Now, you might think like, well, lots of diseases are more common in those groups. So for example, arthritis is the most common cause of pain. It's basically a degenerative disease of your joints, including your back, but also your knee, your hips, things like that. That is more common in Black patients, in poorer patients, but that's actually not the whole story. So let me just tell you why that's not the whole story. So there are a lot of studies that look at patients whose, in this example, we're gonna use the knee, and we're gonna talk about arthritis. So take 2 patients, one Black, one white, and let's find 2 patients whose knee x-rays look the same. They have the same degree of arthritis. And now let's compare their pain scores after we've held constant the way their x-ray looks. Black patients and poorer patients and less educated patients still report more pain, even though their knees look the same. So that's a mystery. And I think the way the literature has solved that mystery largely is to say, well, the source of the pain doesn't look like it's in their knees. Their knees look the same. So what is the source of the pain? Well, maybe it's somewhere else, and maybe it's in their heads. And I actually don't mean this at all in a pejorative way, because a lot of this research is very, very good. Stress tends to make the same physical stimulus more painful. So if you take 2 people, one under more stress than another, and you apply the same amount of pressure to their finger, the person under more stress will report higher levels of pain. Depression and anxiety often manifest as pain. There's also, because of the demands of the rest of the lives of non-white patients, of poorer patients, there's just less mental energy and bandwidth to cope with pain. So that could lead to higher scores. It's also possible that doctors treat these patients differently and give them less access to things that help with pain. But notice that all of these factors have one thing in common, which is that the source of the pain is not in their knee. So let me just walk through a concrete scenario to to give you a sense of how that plays out in the clinic. So a patient walks into your office, you're a primary care doctor, with pain in her knee. You say, okay, well, better get an x-ray and see what's going on in your knee. And what this literature says is that if that patient is Black, it's more likely that the radiologist is going to send you back a report that says, well, the knee looks okay. So what are you going to think? Well, you're going to then say, well, the knee looks fine. I'm going to pursue these other things. Maybe it's stress, maybe it's anxiety or depression, maybe it's something else. And you're not going to refer them to an orthopedic surgeon. You're going to refer them to maybe a psychologist, maybe something else that has nothing to do with the knee. Notice that everything that I've said so far depends a lot on what I mean by, the knee looks the same or the disease severity is the same. How do we measure the severity, for example, of arthritis in the knee? Well, let me show you the current state of the art. This is it. It's a doctor looking at an x-ray and grading that x-ray severity based on accepted criteria in medicine. So what are those accepted criteria? Well, they're based on detailed features of what the x-ray looks like. And the most commonly used grade is called the Kellgren-Lawrence grade. It was developed based on research in the 1940s and 50s by doctors Kellgren and Lawrence, who are here. And they were studying coal miners in England in the 1940s and 50s. And when you go back to those original studies, you find that they don't even mention the race or the sex composition of the study population because they were all white men. That wasn't worth mentioning. So that's where our medical knowledge comes from. And that's what opens the door for this possibility that maybe because of the particular time and place and population on which this medical knowledge was built up, maybe that medical knowledge is missing something that's actually affecting the kinds of patients that we see today who are not all white men. So let me just pause for questions here. So Johanna asks, does this data compare Black and white individuals only? And what would this mean for other ethnicities? And I think this is about the previous algorithm results. So in the paper and specifically in the appendix, you can look at the results for other races and specifically for, this was, again, not my term, but the hospital's term, Hispanic patients. And, on all those graphs, you can basically picture those patients as somewhere in between the Black and white patients. And we found similar results, but less statistically precise for other races. Okay, but back to the knee algorithm. Could there be something wrong with the way we're currently teaching doctors to interpret x-rays? And could there be a way to fix this with an algorithm? So if human radiologists are overlooking causes of pain in these disadvantaged groups, maybe an algorithm can help. And that's certainly a possibility that occurred to us. But if you look at the standard way that machine learning is applied to these kinds of problems, what you find is basically that they train an algorithm to take in an x-ray. So the pixels of the x-ray are the inputs. But what's the output? There's a similar question to the question that was raised with our last algorithm, which is what is the algorithm predicting? And in all of these papers and in the standard machine learning playbook in health, we train algorithms to match human performance. So all these papers are outputting what the radiologist would have said about that x-ray. But notice that's exactly the wrong thing to do if we're worried about humans missing something on the x-ray. The last thing we want to do is to just train the algorithm to spit back out what the human would say. So what's the solution to this problem? Well, here's the current state of affairs. We input the x-ray, we output the Kellgren-Lawrence grade that a radiologist would assign to that x-ray. What we did instead was actually train the algorithm to output not what the radiologist would have said, but what another human whose opinion really matters would have said about the knee, which is the patient. So we, instead of training the algorithm to learn from the radiologist, trained an algorithm to listen to the patient, and on the basis of the way the x-ray appears, predict if that patient would report high or low levels of pain in their knee. Now, finding the data for this kind of thing is unfortunately not straightforward. It's very, very easy to find data sets, and you can find these online, of x-rays linked to what a radiologist would have said about that x-ray, because those data sit in the same place in the hospital computer system, and because in general, we do a much better job of capturing what doctors say about patients than what patients say about patients. We were lucky enough to find a data set that comes from the National Institutes of Health and had the x-rays paired to the patient's pain experience as well as the radiologist reports. And once you do that, you can just take the standard machine learning playbook and swap out the label. So input the x-ray, train a pretty standard convolutional neural net, and output not the radiologist opinion, but the patient's experience of pain. And there's one point that's a little bit subtle, but that I want to make about this, which is imagine that pain was just some random number generator. Imagine it was just like, oh, the patient's in a bad mood, or the patient's under stress, or something else that had nothing to do with the knee. If that was the case, we would not be able to predict pain from the knee x-ray, because stress, what you had for breakfast, which side of the bed you woke up on, none of that is in the knee x-ray. The only thing that's in the knee x-ray is the knee. And if we can predict pain based on that x-ray, it means that that pain is correlated with specific things inside of the knee, with one caveat that I'll come back to in a second. So here's one striking statistic in our sample that echoes something I already told you, which is if we just look at what we call the pain gap, like the excess pain that Black patients have on average, it's enormous. So on this somewhat counterintuitive scale, no pain is 100 and severe pain is less than 86. So if you just look at the difference between Black and white, it's 11 points. So it's over halfway between no pain and severe pain. If we adjust for the fact that radiologists see arthritis more in Black patients, we can actually account for about 9% of that gap. So of that pain gap, 9% of it comes from actual differences in what radiologists see. But when we adjust for the algorithmic severity measure, the algorithmic prediction of pain based on the x-rays, we actually get about half of that gap explained, which is 5 times more than the standard measure of radiologist severity. And we get similar results for income and for education. So there's one set of important things that we need to rule out. And I think this was alluded to in one of the questions about obesity. So we know that a lot of things that we might be able to see in the x-ray are correlated with pain. So race, as I told you, is correlated with pain. Body mass index might also be correlated with pain. So if the algorithm is just reconstructing race and using that as a proxy for pain, it doesn't have to be seeing anything in the knee. It can just be reconstructing someone's race from stuff that has nothing to do with the knee. And so that wouldn't exclude any of these other explanations about stress or the environment or things like that. It turns out we can actually just control for that directly. So what we can do is say, how well does the algorithm explain pain? And if we add in race, does that take away the algorithm's ability to account for pain? And the answer is no, it doesn't. So the algorithm is finding signal for predicting pain that has nothing to do with race or BMI or any of these other things. It's finding fundamentally new things. And we know that because we can actually control for those things directly when we're looking at the algorithm's explanatory power for pain. There are a number of other explanations that I'll just gloss over for now. But here's why this matters. It's because, let's go back to the clinic. When you refer that patient to the next doctor, if that doctor is an orthopedic surgeon and that doctor decides, oh, this patient would really benefit from a knee replacement, that is a life-changing experience for a patient. So your life goes from one where you can't walk around, you can't do your shopping, you can't sit down on the toilet without excruciating pain in your knee, to basically living a normal life. And we know that there are huge disparities in access to those surgeries between Black and white patients. We've always assumed this was about just, the standard factors like access to healthcare and insurance and things like that. But we were also interested to know whether this bias, this underreporting of knee pathology by radiologists in Black patients could also be part of the story. So what we did is we reconstructed the guidelines for who gets access to surgery. So to get access to surgery, you need 2 things. One is severe pain, and 2 is severe disease. So we replicated those guidelines and we saw, okay, under current guidelines, based on the radiologist opinion, how many people would get surgery? Then we swapped in our algorithm for the radiologist as our measure of severity. And when we did that, we would double the fraction of Black patients' knees that would be eligible for these surgeries. So that suggests that part of the story in disparities in access to knee surgery is actually because radiologists are missing causes of pain in the knee that disproportionately affect Black patients. So I want to leave a couple of minutes for questions at the end, but let me just wrap up by saying that why do we want algorithms in medicine? Well, we want to do better than humans. Humans are not perfect. We're pretty good, or at least those of us who trained as doctors think we're pretty good, but we're also very aware that we could be a lot better. And so what we want algorithms to do is not just reproduce our decisions and our biases and our errors, we want to do better. And to do that, we need algorithms that learn from nature, not just from me as the doctor. We want algorithms to learn from the patient's experience of pain, from actual health outcomes. And those data are actually very hard to find, unfortunately. So we were very lucky to have access to the data sets we needed to look at health outcomes and patient experiences, but that's really hard. And so I wanted to mention one way that we're trying to fix that problem is we started a nonprofit organization called Nightingale Open Science, and we're launching that at NeurIPS, which is one of the big computer science conferences in a couple of weeks. And the idea is basically ImageNet for medicine. So ImageNet, if you haven't been exposed to it, is a huge data set of online images that are labeled. So it's a picture of people throwing a Frisbee on a beach, and there's a label that says people throwing Frisbee on a beach. And those labels have been built up by years and years of work of people on Mechanical Turk writing things down like Frisbee, beach, people, things like that. We don't have anything like that for medicine. And that's a huge problem because that's how fields get pushed forward. ImageNet was transformative for the field of machine vision. It let people collaborate and compete on labeled data sets and really built the field of modern machine learning as we know it. And we don't have that for medicine, but we need it. And so this nonprofit is dedicated to building up those kinds of data sets for medicine, pairing images, x-rays, electrocardiograms, things like that, with ground truth labels so that the science of applying algorithms to medicine can move forward. And in closing, here's if you take one thing away from this lecture, here's what to take away. Aiming algorithms at the right target, that choice of label to train the algorithm on is central, but it's unfortunately often overlooked. And it's a huge source of bias, not just in health, but also in crime. Anywhere where we get biased labels, we're going to have this bias. We're often interested in criminal justice and predicting, oh, is this person going to commit another crime? But we don't have someone's innate propensity for crime. We have a variable called arrests or convictions. And those are very biased readouts of someone's innate propensity for crime because of disparities in policing and because of racial bias. This is also just a huge opportunity to push the science of all of these fields forward by training algorithms to teach us about the right labels, not the biased labels that we're currently producing. The people who are going to get this right, I think, are people just like you, people who are not necessarily going to be full-time computer scientists, but who are going to combine data plus some other field that's important to you. And those kinds of people that I think of as like bilingual, people who speak the language of data, but also are deeply immersed in another field, are going to be in very high demand and really, really important. So when you're out in the world and you're in the room where an algorithm is being built or an algorithm is being evaluated, I hope that all of these thoughts are going to help you make the right choice and produce an algorithm that is just and fair and not one that is biased. So let me end there, and happy to go through some other questions. Anything else in the chat or elsewhere? Oh yeah. Does the algorithm in the second example show deficiency in what physicians are looking at? Yeah, great question. So what we're trying to do now is figure out exactly what the algorithm is seeing when the algorithm is looking at a Black patient's knee that looks more painful than a white patient. So we're showing physicians images of one knee that looks very painful and one knee that doesn't. And we're trying to get physicians to look at those images as well and figure out what is different about these things as a way to generate new hypotheses in what the algorithm is seeing and how to push that science forward. If you're interested in health data science, what do you recommend to major in? I think that the way I'd think about your undergraduate experience is this is a great time to learn the technical skills that you're learning in this class. I think that's really, really important. I think there's a lot of time later to learn about particular fields like public health or medicine or criminal justice or finance or anything else. But I would say that you're in exactly the right place in this class, and I would keep going with classes like this. As I mentioned, I teach a class on artificial intelligence for health and healthcare. And that would be another good one to take. But I think building up those technical skills is really critical.
Okay, it looks like we're out of time. Let's all thank Professor Obermeyer for this outstanding guest lecture. Thank you.
Thank you for having me.